Welcome back to section 6 of chapter 4. In this section, we are going to be looking at things called antiderivatives. Now, antiderivative is just going backwards from the derivative. Instead of saying what is a derivative, an antiderivative is basically saying, hey, this is the derivative. What function would have given us this as a derivative? And in this section, we are going to introduce it. This is the next big topic in calculus. We'll be spending the next few chapters on this topic, its applications, how to find them, things like that. Again, this section, though, it's just an introduction. It doesn't get too in-depth, but it should get you a little bit familiar with the idea and the notation as well. And so, we ask, what is an antiderivative? An antiderivative, it's f of x is an antiderivative if the derivative of f of x equals the function for every x in the interval. Typically speaking, we're not too concerned about the interval. We're usually looking at for all x or for all positive or all x not equal to 0, something like that. So the interval part's not hugely important with what we do. But it's just what would give us the function as a derivative. For example, if we had f of x equals 2x, what would give us a derivative of 2x? Think about it for a second. If you're thinking the function y equals x squared plus 729, that is correct. That wasn't the one you were thinking of? All right, how about y equals x squared minus pi? No, that one wasn't the one you're thinking about either. So we have an issue here where the derivative tells us about the slope, but it doesn't tell us anything about what the y values of the function actually are. So because of that, we end up having to use what's called, or what I call, the plus c rule. And what the plus c rule says is that every time you find an antiderivative, you always add c, which is just an unknown constant. In these two cases, my unknown constants were 729 and negative pi. Your unknown constant was possibly 0. If you're thinking y equals x squared gives me a derivative of 2x, that's true. But y equals x squared plus c plus some unknown constant. And what that is, it's the horizontal or vertical translation up an unknown number of units because we don't know where the y values are unless we're given a little bit of information about the function, which we'll talk about a little bit later in this lesson. But in general, you always want to add c to your antiderivatives because we do not know that constant. There's an infinite number of antiderivatives that can come from every function. In addition to antiderivatives, we have what's called the indefinite integral. Now, an indefinite integral is just an antiderivative. That's all it is. They're synonyms. But an indefinite integral is nice because it has some notation that comes along with it. So an indefinite integral, we have this notation right here. The integral of f of x dx equals capital F of x plus c. That means the derivative of capital F equals lowercase f. And so capital F of x plus c is the antiderivative. It says general antiderivative. We'll talk about particular solutions later on, but we can just think of it as the antiderivative or indefinite integral of f of x. Again, the indefinite isn't always put on there. We will be talking about definite integrals later on in a future chapter, but a lot of times if we just say the integral. Also, we can verb that noun. We can use the word integrate. That would be find the antiderivative. Integrate is find the antiderivative. So we could use that as well. So that's what antiderivatives are. Now, how to find antiderivatives? It's just going backwards from a derivative. So we have to think, how do we find a derivative? And then just reverse the process. If we have power rules to find the derivative, we would multiply by the exponent and then subtract 1 to the exponent. Backwards, we're going to add 1 to the exponent and then divide by that new exponent. So the power rule for integrals, we have x to the n, we're going to add 1 to the exponent and then divide by the new exponent. One of the common mistakes people make in this is dividing by the old exponent first and then adding 1. But remember our process to find the derivative, we multiply and then we subtract 1. We have to go do the order backwards. We add 1 and then we divide by the exponent. This is specifically for n does not equal -1. We'll see what happens when n equals -1 in just a minute. But let's look at a couple problems from this first. Let's do the antiderivative of x to the 7th. Well, it's going to be x to the 8th. We add 1. Now we're going to divide by the new exponent, 1/8 x to the 8th plus c. Always plus c. What if we have the antiderivative of 3x to the 5th dx? There's always a dx there, by the way. There should be a dx up here as well. That tells us what variable we are finding the antiderivative with respect to. Generally speaking, there's only one variable in there, but if there were more, any other variable is considered a constant. So we have 3x to the 5th dx. We want to integrate that. We're going to add 1 to the exponent to get x to the 6th, and then divide by that new exponent. So we have 3/6 x to the 6th plus c. And the 3/6 could be reduced to just 1/2 x to the 6th plus c. It works for negative and fractional exponents as well, as long as it's not -1. So we could say, what's the antiderivative of x to the -1/2 dx? We're going to add 1 to the exponent. So -1/2 plus 1 is going to be x to the 1/2. Divide by the new exponent. When we divide by 1/2, that's the same as multiplying by 2 plus c. You can always check it by taking the derivative. If we take the derivative, 1/2 times 2 is 1, subtract 1, we get -1/2. And the plus c is a constant, it goes away. So now let's see what happens if we have n equaling -1. So let's do the antiderivative of x to the -1 dx. So if we're doing it using the same method, we're going to add 1. So we're going to get x to the 0, which is a constant, divided by the new exponent, which is 0. We have something divided by 0. This doesn't really work out. It's meaningless, is really what this is. So how did we get x to the negative 1 as a derivative? Because we have gotten x to the negative 1 as a derivative. Maybe if we rewrite that, instead of x to the negative 1, remember that equals 1 over x dx. How do we get 1 over x as a derivative? It doesn't come from a power function. It comes from the natural log. The integral of 1 over x dx is equal to the natural log of x. It's technically the natural log of the absolute value of x because x has to be positive inside the natural log. Generally, we don't have to worry too much about the negative situation here just because it doesn't usually come up, but we do want to make sure we have those absolute value bars. And then plus c, the plus c always goes to the very end. Whatever it is you're doing, the plus c is at the very end. And this is for all x that isn't equal to 0. Because we can't have the natural log of 0, it has to be greater than 0. And 1 over 0 doesn't exist anyway, so having that as a derivative doesn't make sense. So it has to be when x does not equal 0. Some properties that will be useful. We have the sum property, which means the antiderivative of something plus something. We can split it up and do each piece separately, just like we find the derivatives of each piece separately. If we had x to the 7th, if we had the x to the 7th plus 3x to the 5th, the answer would just be 1/8 x to the 8th plus 3/6 x to the 6th plus c. We would just do each piece separately plus c on the end. And then the constant multiple property. If we're multiplying by a number, we could just move that number out in front. Example of this one was this 3. On that one, it just stayed here. We had 1/6 times x to the 6 times the 3. It just multiplies onto the front. So these are the same as the properties we have with when we're finding the derivative. Same thing, just backwards. So let's look at some more antiderivatives because we've dealt with a lot more functions than just power rule. We've dealt with trig. So we have, remember, trig integrals or trig derivatives. Cosine gives us negative sine, so the antiderivative of sine gives us negative cosine. You might think the derivative of sine is cosine, so the antiderivative of sine is cosine. No, because if we found the derivative of this side, the cosine gives us negative sine, we need that other negative to make this a positive over here. So always going backwards to check to make sure that you have everything you need is a good strategy, and we'll use it in a minute when we get to things that are a little bit harder. The other ones, the antiderivative of cosine equals sine. The antiderivative of secant squared of x is tangent because the derivative of tangent secant squared. And then same thing for these other ones. Now remember that we can use chain rule in these as well, and very often we do. Usually we don't just have sine of x or cosine of x. Usually we're going to have something with something more in it than just x. Now those can get very complicated very, very quickly. We're not worrying about that so much today. What we're worried about is when we have linear transformations on the inside. So we're going to have something times x plus something. No x squareds, no sine of e to the x, no sine of cosine of x, just things like sine of a number times x plus b, cosine of a number times x plus b. If we were to take the derivative of something like that, we'd have cosine of kx plus b times the derivative of that, which would be k. So to get rid of that, instead of multiplying by k, we have to divide by k, and that's where you get these things over here. The b being a constant, the derivative of the b is nothing. So we don't have to worry about that. It still stays inside the trig, because just like when we take the derivative of a trig function with chain rule, the inside does not change. Same thing when we take an antiderivative. The inside of the trig will not change. But we divide by that k. Other than that, notice the antiderivative of sine is negative cosine, just like it was up here. So those aren't changing. And we still have the plus c. Again, notice it goes to the very end, the outside. It's not part of the inside. It's not the cosine of kx plus b plus c. The plus c is just on the outside, sitting at the very end of everything else that you have. So those are some trig antiderivatives, and it's really just plug it into the formula type stuff. Another one, we have exponential integrals. E to the x, it's its own derivative. It also happens to be its own integral. So the antiderivative of e to the x is e to the x plus c. We could get some chain rule involved in that. Or well, a to the x. The derivative of a to the x is a to the x times the natural log of a. Well, to find the antiderivative, we divide by the natural log of a. And now chain rule. E to the kx plus b, it's same thing, it's just a linear thing. So the derivative of that's just going to be k. If we were finding the derivative, we would multiply by that derivative. So finding the antiderivative, we divide by that derivative, just like with the trig stuff. Same thing if we have a to the power. And so those are finding antiderivatives. So we're going to find antiderivatives, but we're also in the process, we're going to use what's called initial conditions to find a particular solution. And all that means is that we're going to be given an equation, and we're going to be given a point on the actual function. We're going to plug it in to solve for c. That's all that is. It's not like calculus. It's just plugging it in to figure out what c equals. And that's called a particular solution because it's that one solution that will go through that point, as opposed to the general solution, which has the plus c that accounts for all of them. So a question could look like, solve the differential equation with the given initial condition. A differential equation is just an equation with a derivative in it. What we're doing will be the derivative equals something. So dy over dx equals something. Later on in the year, we'll get to things that have the derivative inside of the equation itself. That's when things get really fun. But right now, it's just, again, getting you used to some of the terminology and stuff like that. So we have dy over dx equals 3x to the fifth plus 4. And then the initial condition, y of 1 equals 7. So first step, we have to figure out what y equals. Now technically, in this step, we don't usually show, but we're going to multiply by the dx here. So we get dy equals 3x to the fifth plus 4 dx. Does this look kind of like implicit differentiation? Kind of. It kind of is. But again, this is a step that we don't normally show when we're finding the derivative. We also don't normally show it when we're finding the antiderivative. But then we would take the antiderivative of both sides. What's the antiderivative of dy? The antiderivative of the derivative of y is just y equals. And then the antiderivative here, this is where we can split it up, do each piece separately. 3x to the fifth, well, that's going to be an x to the sixth, and divided by 6, that 3 sits there still. And then plus 4 will give us a derivative of 4. That's 4x to the 0, add 1. The derivative of a constant, or the antiderivative of a constant, is just 4x, or the constant times x, plus c. And so this is y equals 1/2 x to the 6 plus 4x plus c. That's the general solution. Now we're going to plug in our initial condition. So we'll have 7 equals 1/2 1 to the 6 plus 4 times 1 plus c. So 1 to the 6 is 1 times 1/2 is 1/2 plus 4 is 4.5. 7 equals 4.5 plus c. Subtract 4.5. You get 2.5 equals c. Plug that back into our general equation. We get y equals 1/2 x to the 6 plus 4x plus 2.5. That is our particular solution. That is the one solution, the one antiderivative of this differential equation that will go through that point. So again, you find the antiderivative, and then you just plug your point in for c, find c, plug that back in. The only calculus step is this one right here. So that's using the initial condition. It's possible we could use the initial condition more, or we could find the antiderivative more than once. For example, if we have a second derivative, we need to find the derivative and then the regular function. Where might this come up? I don't know. Where do we have functions, derivatives, and second derivatives with meaning? Maybe if the second derivative is an acceleration function, and then you know something about the initial condition, and then something about the actual function. If you're dropping something, your acceleration is gravity. You know that, it's constant. You can find the antiderivative to get your velocity, plug in a point that you know about velocity, such as perhaps the initial velocity. How fast was it going when whatever it was released, either from your hand or a cannon, and then you can find the antiderivative of that to get your position function. And it allows us to do a lot more with that topic. So how do we do this? The first one, we're just going to find the antiderivative of our second derivative. So f prime of x will equal the antiderivative of x cubed minus 2x plus 1 dx. That's a cubed. And so f prime of x equals, we have to add 1 to the exponent, so that'll be an x to the 4th, then divide by the new exponent, minus add 1 to the exponent, that's x squared, divide by the new exponent is 1 plus 1x plus c. There's our first derivative, which would be the first antiderivative we're taking. Sometimes when we're doing this more than once, we'll have like a c1 to differentiate it from the next c, which will be c2, especially if we were to just do the antiderivative from here and we'd have two c's in the same equation. That gets a little bit weird. I would put in the initial condition at this point, however. So f prime of 0 equals 1. So that's going to be 1 equals 1/4 times 0 minus 0 plus 0 plus c. So c equals 1. Plug that back in there. F prime of x equals 1/4 x to the 4th minus x squared plus x plus 1. And now we're going to find the antiderivative of that. F of x will be the antiderivative of 1/4 x to the 4th minus x squared plus x plus 1 dx, which we're going to add 1 to the exponent, x to the 5th, divide by the new exponent, 1/4 divided by 5, multiply the denominator with the 5, that's going to be 1/20th, minus, this will be an x cubed, divide by the new exponent, 1/3. You notice how I kind of do that not in linear order. I do the exponent, then I go back in front to figure out the coefficient. And then plus, we have an x squared, so 1/2 x squared, plus 1x, plus c. Plug in our initial condition, 0, 0. So if I make this 0 and everything else 0, that's going to be c equals 0. So our particular solution will just be the same thing, 1/20th x to the 5th minus 1/3 x cubed plus 1/2 x squared plus x, and c will be 0. And so that's using initial conditions. If this was an acceleration velocity position function, it would probably ask you a question about velocity or position or distance traveled or something like that. In this case, it was just find those two. So this is an introduction to antiderivatives. This is how we're finishing off chapter 4. And that's basically what we're doing. So keep working problems, keep asking questions, and as always, happy mathing.